Welcome back to the podcast, everybody. This is example 11.7. Now, I know it originally says here 11.6, but in your notes it should say 11.7. And we're talking about centripetal acceleration and centripetal force and all things related to that. So this is an interesting problem, or actually an interesting statement. And the statement is that the rotation of the Earth, in fact, makes us feel lighter depending on where we are. So let's say we have the Earth right here, and it's spinning around. Okay, and here's the North Pole right here, and here's the South Pole. And I didn't draw it perfectly circular, but that's actually good because, believe it or not, and this is an earth science fact, the Earth, in fact, bulges kind of at its equator right here because it's spinning around. If you were to take a water balloon and spin it around on its axis, it would actually bulge out because of centripetal force. And so the statement here is saying that a person standing on the equator is actually going to weigh slightly less than a person here standing at the North Pole. Because why? Well, because this person is being whipped around the Earth fairly quickly, and this person right here is really, unless they're standing, well, if they're standing exactly at the North Pole, they won't be moving at all, but if they move a little bit from the North Pole, they will be moving around very slightly, but not nearly as much as this person right here. So the person at this North Pole is essentially experiencing no centripetal acceleration or centripetal force by the rotation of the Earth. The person here at the equator is. So that's the equator, and this is going to be North Pole right there. So let's write down what we know about this person. Our mass equals 100 kilograms. Okay? And the Earth's radius of the Earth is 6,371. Is that right? Yeah, 0.1. I'm sorry, 6,378.1. Oh, great, thank you. Sorry about that. 78, sorry. 0.1 kilometers. All right, now that's a lot bigger unit than we want, so we need to convert that to meters. So we need to multiply that by 1,000. So it would be really 6,378,100 meters. Because meters is our standard unit of length for standard unit for length or for radius. If you want to shorten this down, you could say, well, now let's not scientific notation it. Let's use all the digits right there. Okay, that's going to be our radius of the Earth. And I'm going to draw this here, this Earth here again, so we can label it a little better. Okay, here's our person on the North Pole, and here's our person right here on the equator. All right, now both people are feeling a downward force of gravity, mg, and this is down for that person, mg, right here. But since the Earth is rotating on around that axis right there, this person is going to feel a force. Well, I guess I should say the rotation of the Earth is actually causing them to sort of be thrown out into space to the tune of whatever centripetal force is there. Like, for example, if you're on the gravitron or something like that, you feel thrown out towards the outside of the machine. People call that centrifugal force. Well, it doesn't really exist, but you feel that because you want to move in a straight line, and so you want to shoot off out into space right here. Now the gravitron's walls keep you in, but really, since we're standing on the outside of the Earth, there's nothing really to keep us in other than the inward pull of gravity. So if it weren't for the inward pull of gravity, we would just shoot off out into space right there. So the centripetal force, really, or the force caused by the acceleration of us being whipped around the Earth, is really acting against the inward pull of gravity right here for this person on the equator. For this person here at the pole, at the North Pole, there is no force because they're not moving around the Earth. They're just sitting right on top of it. It's kind of like saying you have an ant at the edge of a turntable and an ant at the very center of a turntable. Which person is experiencing more, which ant is experiencing more centripetal force or acceleration? What's the one on the outside or on the edge? So this person here has these two forces acting against each other, and this person here at the North Pole has the two forces. It only has the one force. So, enough talk. Let's just start calculating this. A asks us, what is the weight of the person at the North Pole? Okay, well, the weight force, that's simply your mass times acceleration of gravity. So for that person, it would be 100 kilograms. It's late. Times 9.81 meters per second squared. Okay? And that means that person would have a weight of 981 newtons at the North Pole. Okay? But part B says, what is the weight of the person at the equator? Okay, well, the weight of the person at the equator, I should say this is, that should be N and this should be E right here. Remember, we had these two forces acting against each other. So it's going to be their weight force minus the centripetal force that would exist for that person there spinning around the Earth. And now we can calculate that. In fact, let's just write it up here. The centripetal force acting on that person is what we have the radius right here, and we have I jumped ahead. Well, I didn't really jump ahead. I just I didn't write a few other knowns down. Let's go back up here a minute. Okay, so we want to find. Let's take a break from part B and focus on what is the centripetal force here of this person, right here. Okay, well we want to find the centripetal force. We know the mass of the person. We want to find really the centripetal acceleration of this person here at the equator. Okay, we don't know the velocity, and all we know is the radius. Do we know anything else? Well, we actually do. We know the period, right? We know the period of the Earth, T, and that is, we're going to say 24 hours. It's actually slightly different depending on what you're talking about, but never mind, that's more earth science stuff. We're going to say 24 hours. So let's convert that to seconds. 24 hours, 1 hour. 1 hour to... We can do this in one step. We know that it's 1 hour to 3,600 seconds, right? And that gives us, for a whole day, for a whole rotation of the Earth. What's that? 86,400 seconds. Now that will enable us to find the centripetal acceleration of the person at the equator. Why? Because that, if we look at our equations, that's 4 pi squared times r divided by the period squared. So that would be 4 pi squared times r, radius of, here we go, 6,378,100 meters, divided by our period of 86,400 seconds. That value squared. Okay? So that will give us a centripetal acceleration of 0.03, let's say, I'll go 3 digits, 337 meters per second squared. Okay? So let's put a dotted line box around that. We need that because we need to solve for what the centripetal force would be, so we can subtract it from the weight force and find out what the person would actually weigh at the equator. So that's going to be mg minus, what is our centripetal force for that person? Well, it's that person's mass times 0.0337 meters per second squared. Oh darn it, I didn't even write in G. Okay, well that's all right. Well, we can either multiply it like this, or we can factor out the m. We can say the mass times G, or 9.81 meters per second squared, minus 0.0337 meters per second squared. And I should just write the m, the mass. Sorry. That's just 100 kilograms. And that'll give us the weight of the person at the equator, because the outward tendency of motion caused by the centripetal force is going to be acting against the weight of gravity. And that is 978 newtons. Okay, so we have a clear difference in our weights, or you might say the net force caused by gravity, depending on if you're at the equator or at the poles. And so the answer for C is, as latitude increases, that is, if you go, the equator is 0 latitude, and if we go towards the poles, your latitude increases. As latitude increases, your weight increases as well. There we have it. Example 11.7. So if you want to drop a few newtons, just go to the equator. Can't you see?